Have you heard about the infamous big O notation? Did your friend ever complain about how confusing time complexity are? Well, they are indeed. If you're nodding your head right now, today's episode is just for you. We will help you master the 3 most common time complexities. Let's go over one by one.
But why should you care about time complexity? Understanding time complexities help you write more efficient code, save computational resources, and ultimately, it could help you land the dream job at the big tech company. So what is time complexity? It's an estimation of the time it takes for an algorithm or a function to run. It's measured based on how the running time increases as the size of the input increases. Time complexity can be constant, logarithmic, linear logarithmic, quadratic, and so on. But today, we are going to tackle these 3 most common time complexities.
First, we have a constant time complexity, denoted as O1. It means that the running time doesn't change as our input data size increases. The common use case for constant time complexity are, first, simple array access. For example, we have a simple array here from 0 to 9. By the way, the array here is a list. List is one type of array in Python. But keep in mind, there are other types of array that are not lists, such as NumPy array. Now, if we want to access an element, let's say the second element of the list, no matter how large the list is, it takes the same runtime. Another example you might have heard about is called hash table. Hash table is nothing more than just a dictionary in Python. Any type of a hash table insertion is often constant time complexity. That's because a hash function is used to decide where in memory to store the value for a given key. And this operation does not depend on the size of the hash table. Pretty straightforward, right? Now let's level up to a more complex time complexity, which the binary search is based on. Before we move on, don't forget to like and subscribe to our channel. We really need your help. Next, we have a logarithmic time complexity, represented as O log n. It means the running time increases logarithmically for an increase in the input data size. A common example of this is binary search, which is a search algorithm that finds the position of a target value within a sorted list. It compares the target value to the middle element of the list, and based on the comparison, it can discard half of the search space. This process is repeated until the target value is found or the remaining search space is empty, making its time complexity logarithmic. Let's take a look at the sample binary search code line by line below. First, we are defining a binary search function. It takes 2 arguments, a sorted list, A list, and our target value that we are looking for in the A list. Then we are initializing 2 pointers here, left and right. These represent the start and the end of the list. Left is 0 because it's the first index in the list. Right is length of the A list subtract 1 because that's the last index in the list. Next, we start a while loop as our main search loop. We will keep searching as long as the left pointer is less or equal to the right pointer. We then define a mid-pointer, which is the middle index of the current list. The / operator here means integer division. This line is checking if the middle element of the list is equal to our target. If it is, we have found our target and return. If the middle is less than our target, that means our target must be in the right half of the list. And we can move our left pointers to 1 past the middle index for the next loop. If the element isn't less than our target, that means our target is in the left half. We move our right pointer to 1 before the middle index to start looking in the left half. If we have exit the while loop, that means our left pointers has crossed our right pointers and we couldn't find the target. In this case, it returns target not found. As you can see, with each iteration in the while loop, we are cutting our problem size in half. So that's logarithmic time complexity for you. If you are interested in learning more use cases, we are making another video on binary search tree. So be sure to subscribe to our channel and turn on the notification. Moving on, we have linear time complexity, denoted as ON. This means that the running time increases at the same rate as the size of the input. Some common use cases are if you want to find the maximum value in a list, or the common algorithm like linear search. Linear search is looking for a specific item in a list. In the worst case scenario, you will need to check every item in the list, which makes it a linear time complexity. There you have it, folks. We've just cracked open the mysterious world of time complexities. Understanding these fundamental ones will not only help you improve your coding skill, but also give you a head start when studying the more complex ones. Remember, every great coder was once a beginner who kept on learning. Before we end, let's do a quick recap. Today, we looked at example of constant time complexity like simple array access and hash table insertion. Then, we dived into the world of logarithmic time complexity, where we used binary search as an example. And lastly, we tackled linear time complexity, where we used linear search and finding the maximum value in a list as examples. You can find all of the example code details in our video description below, so don't forget to subscribe to our channel and turn on the notification so you won't miss our future episodes. We're excited to explore more fascinating topics in Python with you, so stay tuned and happy coding. See you next time.